Hello everyone, welcome to Modern Optimization Methods. In this part, we will introduce the fifth part of Chapter 2, the search directions. This part includes the three kinds of directions, Newton's direction, quasi-Newton's directions, as well as conjugate gradient directions. Now, firstly, let's talk about Newton's directions. So, Newton's directions actually given by the formula like this. So we have pkn. Here this capital N represents Newton's direction. It is given by the inverse of Hessian matrix at xk, then multiplied by the gradient of f at xk. And then we take the minus direction. So this is Newton's direction. It seems that the calculation is a bit complicated. So let's first introduce the intuition why we can have this formula. The intuition is by the Taylor's expansion of fxk plus p at xk. So we can expand the function value of f to its second order, and we basically approximate this function f by the second order quadratic functions. Okay? So if we take p as our variables and we take expansions, then the first term is fxk as before, the second term is gradient, and the third term is the Hessian matrix of f at xk. Okay? So we write the right-hand side of this equation as the mkp. It is a function, and we are looking for the direction p. So if we try to minimize this mkp, then we will get the Newton's direction. So if I draw a picture geometrically, it will give you the following result. So we assume that we got a function here. This is f, right? And we assume we get xk here, right? Then basically Newton's direction says, okay, we start at xk and we approximate this function curve by a quadratic function, all right? So this is the quadratic function, and xk is here, right? So instead of minimizing this fx, we minimize this quadratic function. So the function will return us an xk here, xk plus 1 here, right? So the direction from xk to xk plus 1 will be the Newton's direction here, all right? So this gives us the intuition of Newton's direction. Geometrically, it means that we approximate function at a point xk by a quadratic function, and we solve this quadratic function to its minimizer. The direction between xk and xk plus 1 will be the Newton's direction. Okay? Now, we have several remarks about Newton's direction. As we can see that we approximate this function by a quadratic one at a neighborhood of xk. Okay? So if this approximation is within a small region, then it is very reliable. All right? So this corresponds to the first remarks. Newton's direction is reliable when f, this curve, and the quadratic curve are approximate to each other very well. Okay? The second remarks basically means that Newton's direction is a descent direction under some conditions. Okay? So recall that we have mentioned what is descent direction in the previous class. Okay? It basically says that the direction take the inner product with the gradient must be strictly smaller than 0. If we take Newton direction to do the inner product, then under some conditions, we will have this inner product smaller than 0. So what is the condition? Okay, so we have several conditions actually to make Newton's direction exist. Firstly, the Heysen matrix must be invertible. Secondly, the Heysen matrix must be positive definite to guarantee the sufficient decrease. Okay? So these are two assumptions to make Newton's direction a descent direction. The third remark is that in this case, we actually take the step length to be unit step length. Okay? And we can also modify it to not unit step length. Okay? Meaning that we can add a line search strategy. We will talk about the details later in chapter 3. Now, we can show that the quadratic convergence actually holds. So what is quadratic convergence? We will introduce this in the last part of chapter 2. However, disadvantage is that for Newton's direction, it may have heavy computational cost. Why? Because it involves the calculation of Heysen matrix. All right? So recall that Heysen matrix, it is a matrix of n by n, meaning that you have to calculate n square elements in this matrix. All right? So it involves computational cost, which is very heavy. Now, let's take a look at the quasi-Newton directions. Given the fact that Newton's direction have a lot of requirements, for example, it requires the inverse of Heysen matrix exists, and also it requires that the Heysen matrix must be positive definite. So can we modify a little bit to get around these conditions? So this comes the quasi-Newton methods. So in quasi-Newton methods, we do not use the Heysen matrix directly. Instead, we use the matrix BK to approximate the Heysen matrix. So this gives the quasi-Newton direction PK, as I showed in this equation. And we replace the Heysen matrix by an approximate matrix BK. Okay? So the advantage of quasi-Newton methods is obvious. Firstly, it does not require the calculation of Heysen matrix because we use the BK instead. Okay? And meanwhile, it still keeps a superlinear convergence rate, which is fast. Finally, you may ask how we can get this BK. By which way we can approximate the Heysen matrix very well. So this comes that why we use the quasi-Newton methods. So the main idea is that we approximate Heysen matrix by BK firstly, and the second one is that how we can get the next Heysen matrix approximation, that means BK plus 1. How we can get the next approximation. So this is very important. All right? In this page, we will mainly discuss how we can derive BK plus 1 based on BK. So actually, BK has to satisfy some conditions. Now, the first condition is that it must satisfy the following second condition. That means BK plus 1 in SK direction will be the same as YK. So what is SK? SK is the difference of the two successive iterations, and YK is the difference of the two successive gradients. All right, So BK, the second equation, basically says that the BK along the direction SK, okay, after multiplication, then it must be the same as YK. So this is one condition that we can use to get the next BK plus 1. The other condition is that this BK plus 1 must be symmetric, all right? And also, we must make sure that when we generate BK plus 1 from BK, the computational cost must be small, or which means that we can make that the difference between the two matrices must be low rank, all right? In other words, we can make a bit modification to BK to get BK plus 1. Based on the several rules here, we propose a class of quasi-Newton directions. Okay? Notice that the above three conditions does not lead to unique BK plus 1. It leads to a class of BK plus 1. So we called the quasi-Newton methods as methods rather than method. Okay? So there are two most popular updating formula, which I list here. The first one is called the symmetric rank 1 update, short for SR1. It actually modified BK by a rank 1 modification, and then we can reach BK plus 1. So if we take a look at the second term here, it is actually a rank 1 matrix. Why? Because we can take this vector yk minus bksk as a vector. Then this vector multiplied the transpose of this vector will become a rank 1 matrix. Okay? And the denominator here is a constant. So totally speaking, this BK is a rank 1 update. All right, let's take a look at the second update formula, the BFGS formula. It was originally proposed by Broyden, Fletcher, Goldfarb, and Schnell. Okay? It is actually a rank 2 modification. So why this modification is rank 2? If we take a look at this formula, we find there are two terms after BK. So each term actually is a rank 1 matrices. So it is a rank 2 modification. Now, let's talk about the inverse of BK. Recall that in quasi-Newton directions, BK is the approximation of Hessian matrix. So, actually, in quasi-Newton direction, we need the inverse of BK. Therefore, is it possible to derive an update formula for the inverse of BK? The answer is yes. We use H to denote the inverse of BK. Then we can get the following corresponding update formula for HK. Okay? So HK is the inverse of BK, and we can similarly have the two updating formula for the inverse of BK. So HK plus 1 is modified by a rank 1 constraint. Okay? And for the BFGS formula, the update tends to be a little bit complicated. However, it is still rank 2 update. All right? So this is the update formula for quasi-Newton methods. Now, let's take a look at the third direction, conjugate gradient direction. In conjugate gradient direction, from the name, you can see that it is related to gradient. Okay? There is also some conjugate involved. Conjugacy will be introduced in chapter 5, and we do not introduce the notation here. Okay? So I just give the formula for the conjugate direction it actually has the form like the sum of two vectors. The first vector is the steepest descent direction, which is kind of gradient. The second vector is a pk minus 1. Okay, this pk minus 1 is actually the previous direction. Okay, so recall that we have current direction as pk, so pk minus 1 is the previous direction. All right, so this is the update for conjugate gradient direction. It is kind of a combination between the previous update direction as well as the current gradient direction. And what is the intuition for conjugate gradient direction? You may ask this question. Actually, conjugate gradient directions were originally proposed for solving the linear system here, ax equals b, where this a is positive definite. And actually, we can show that this linear system is equivalent for solving the quadratic optimization problem, which is a minimization problem here. Okay, so this is the connection between solving linear system as well as solving optimization problem. Now, what is the benefit of the conjugate gradient directions? As we can see from the direction, it is actually only involves gradient information and the previous directions. So the computational cost is very cheap. This is one advantage. On the other hand, it actually needs less storage, okay, because it only involves vectors. Moreover, it is much more effective than using the steepest descent direction. Okay, so this is compared with the steepest descent direction. It will be more efficient than the steepest descent direction. Actually, it is a very powerful direction to solve the optimization problems. We will demonstrate more details in Chapter 5. Now, let's make a brief summary about this part. In this part, we mainly talk about 3 search directions. All of them are descent directions under some conditions. Okay, so the first one is Newton's direction, and the second one is quasi-Newton direction, and finally the conjugate gradient direction. So together with steepest descent directions, they are the search directions under the line search strategies. Okay, so in the next part, we will introduce the trust region strategy, which is another way to update the next iteration. All right, we stop here and see you next time.